Have you ever wondered what happens when a computer operation exceeds its limit? Well, in the world of computing, there's a term for this phenomenon: overflow. Overflow is an intriguing concept, representing situations when the result of an operation surpasses the range or capacity that can be symbolized by a particular data type. It's as if you're trying to pour a gallon of water into a pint glass. There's bound to be spillage. Overflow isn't confined to one type of operation. It can pop up in a myriad of operations, from the simple act of addition and subtraction to the more complex multiplication and division, and even other arithmetic operations. The data types involved can also play a significant role in the occurrence of overflow. It's like trying to fit a square peg into a round hole. Sometimes, the data just doesn't fit the mold. But why should we care about overflow? Well, think of it this way. Imagine you're running a marathon. You've been running for hours, and you're near the finish line. Suddenly, your stopwatch resets to 0, and all your hard-earned progress is lost. That's essentially what happens during overflow. The system loses track of the true value, and the result can be far from what you'd expect. Overflow can have serious consequences, especially in critical systems where precision and accuracy are paramount. It can lead to unexpected results, cause software to crash, or even open up security vulnerabilities. It's like a ticking time bomb in your code, waiting to explode at the worst possible moment. However, fear not. Overflow isn't an insurmountable problem. With the right understanding and techniques, you can manage and even prevent overflow, ensuring that your software runs smoothly and reliably. It's all about understanding the limits and knowing how to work within them. So buckle up and prepare to dive into the fascinating world of overflow. In this journey, we'll explore the different types of overflow, uncover techniques for handling overflow, and share best practices to keep overflow at bay. Next, let's delve into the different types of overflow. Overflow isn't just one size fits all, there are different types to consider. To start with, let's look at integer overflow. This is what happens when the result of an arithmetic operation exceeds the maximum value that can be represented by the data type. For instance, if you're working with a signed 32-bit integer, adding 1 to the maximum value, which is 2 to the power of 31 minus 1, will result in overflow. Next up, we have floating point overflow. This occurs when the result of a floating point operation exceeds the maximum representable value, either positive or negative, for the data type. Floating point overflow can occur during addition, multiplication, or other arithmetic operations. For example, imagine you're multiplying two very large floating point numbers. If the result is larger than what can be represented by the floating point data type you're using, you've got yourself a floating point overflow. Last but not least, there's stack overflow. This happens when the call stack of a program exceeds its maximum size. It typically occurs due to excessive recursion or deeply nested function calls. In other words, if your program keeps calling functions within functions within functions, well, you get the idea. The call stack can get too big, and boom, stack overflow. To give you a real-world analogy, think of these types of overflow like a coffee mug. Integer overflow is like pouring too much coffee into your mug, it spills over the top. Floating point overflow is like adding too much sugar, it won't dissolve and just sits there at the bottom. And stack overflow is like stacking too many mugs on top of each other. Eventually, they topple over. Now that we know the types of overflow, let's discuss how to handle them. Overflow might seem like a daunting problem, but it can be managed with the right techniques. Take, for instance, the technique of checking for overflow before performing an arithmetic operation. This involves comparing the operands or checking the result against the maximum and minimum values that can be represented by the data type, thereby averting a potential overflow scenario. Another technique is saturation arithmetic. In this method, the result of an arithmetic operation is clamped to the maximum or minimum representable value if an overflow would occur. This effectively prevents the result from exceeding the limits of the data type, thus keeping overflow at bay. Then there's modular arithmetic, where the result of an arithmetic operation is computed modulo a specified value. This can prevent overflow by wrapping around to the beginning of the range when the maximum value is exceeded. Think of it as a clock striking 12 and then starting back at 1. Next, we have exception handling. Some programming languages and environments raise an exception or trigger an error when overflow occurs. This allows the program to detect and handle overflow situations explicitly, making it easier to troubleshoot and resolve overflow issues. Last but not least, we have compiler options. Some compilers provide options or flags to enable overflow checking during compilation. This can help detect potential overflow issues at compile time and generate appropriate warnings or errors. It's like having a watchful guardian that alerts you of any potential overflow threats. These techniques can help handle overflow, but there are also best practices to keep in mind. Always remember, the best way to handle overflow is to prevent it from happening in the first place. So stay tuned as we delve into the best practices for overflow handling in the next scene. Let's continue our journey towards mastering the art of overflow handling. Overflow handling isn't just about fixing problems as they occur, it's about preventing them in the first place. When it comes to best practices for overflow handling, the first thing to consider is to use data types with sufficient range. This means choosing data types, such as larger integers or floating point types, that can accommodate the range of values expected in your application. This can help to minimize the risk of overflow. For instance, if you are working with extremely large numbers, using an unsigned 64-bit integer instead of a signed 32-bit integer could be a wise decision. Next, it's important to perform range checks. Before performing arithmetic operations on user input or external data, it's crucial to validate the input values to ensure they fall within acceptable ranges. By doing so, you can prevent overflow before it even has a chance to occur. Then it's about handling overflow gracefully. If overflow does occur, it's important to handle it in a way that doesn't disrupt the user experience. This could involve providing meaningful error messages, logging the overflow event for future analysis, or taking appropriate corrective actions based on the application requirements. The key is to ensure that your application is resilient and can recover gracefully from overflow situations. Finally, don't forget to test for overflow. This involves testing your code under various scenarios, including boundary cases, to ensure that your overflow handling mechanisms are working correctly and efficiently. It's not enough just to have overflow handling measures in place. You have to make sure they work too. So, to sum up, the best practices for handling overflow are: use data types with sufficient range, perform range checks, handle overflow gracefully, and test for overflow. By taking these steps, you can help to prevent overflow from occurring, and if it does occur, you can ensure that your application handles it effectively. Following these best practices can help ensure the robustness and reliability of your software applications. Overflow might seem complex, but with understanding and careful handling, it can be managed effectively. In the past few minutes, we've navigated the labyrinth of overflow, exploring its various types: integer overflow, floating point overflow, and stack overflow. Each type has its unique characteristics, but the common thread is the potential to exceed the capacity of a given data type during operations, thereby causing errors in your software. We've also delved into the toolkit for handling overflow, checking for overflow before performing operations, using saturation arithmetic to limit results within the data type's range, and employing modular arithmetic to wrap around results are just a few techniques at your disposal. Exception handling and compiler options too offer robust ways to detect and manage overflow situations. But remember, prevention is always better than cure. Choosing the right data type with sufficient range right from the start can save you a lot of trouble down the line. Similarly, performing range checks on user inputs and external data can nip potential overflow issues in the bud. When overflow does occur, it's crucial to handle it gracefully. Clear error messages, diligent logging, and appropriate corrective actions can turn a potential crisis into a manageable situation. And of course, testing your code under various scenarios, including boundary cases, is the final line of defense against overflow errors. The journey to mastering overflow is a gradual one, requiring both understanding and practice. But it's a journey well worth undertaking. By implementing these techniques and best practices, you can enhance the robustness and reliability of your software applications, making them more resilient in the face of overflow errors. As we conclude, remember that handling overflow is critical to the robustness and reliability of your software, so next time you code, keep these points in mind. Thank you for watching.